everyone, so we're solving this problem here, number 35. So here we have a projectile being fired with an initial speed, let's see if we can read this a little bit better. An initial speed of 75.2 meters per second at an angle of 34.5 degrees above the horizontal along a long, flat firing range. We want to A, determine the maximum height reached by the projectile, B, the total time in the air, C, the total horizontal distance covered, i.e. the range, and D, the velocity of the projectile 1.5 seconds after firing. All right, so the best way to solve this problem is going to do it step by step. So the first thing, we draw a diagram. All right, so we have some sort of horizontal firing range where a projectile is traveling in a parabolic shape. We are given some initial velocity at some angle. Right, so I'm going to write these as known values here, kind of separate from my x and y. My initial velocity, we're told that was 75.2 meters per second, right, at an angle of 34.5 degrees. And I'm also going to list here my coordinate system. I'm going to call this corner here 0, 0. My positive y is going to be upwards. My positive x is going to be to the right. I can foresee in this problem, since we're given our initial velocity, which is at an angle, that's not directly in our x or y directions, where we are most likely, and we will be, needing to break up our initial velocity vector into its x and y components. So I'm going to write an expression for that now, since v naught and theta are both known values. Right? So I'm going to draw here my exaggerated initial velocity vector. We can break that up into a piece acting horizontally and a piece acting vertically. These both vectorially add in the tail to tip method to become this resultant vector of v naught. So this piece here is in our x direction, so that's my initial velocity in the x direction. This piece here is our initial velocity in the y direction, and this angle here is theta. So we can write, or we can look at, let's pick a trig function. So if you look at sine of our angle, sine is opposite of hypotenuse. So my opposite is initial velocity in the y direction. My hypotenuse is my initial velocity. All right, so we can rewrite that to say that my initial velocity in the y direction is the same thing as saying my initial velocity times the sine of theta. So there's my expression. I can write and crunch these numbers out. I'm not going to. Cosine of theta, that's adjacent over my hypotenuse. So that's my initial velocity in the x direction divided by my initial velocity. So that can be rewritten and solve for my initial velocity in the x direction. That's going to be my initial velocity times the cosine of theta. Right? And just in case you decide you do want to crunch those numbers out, I did do that earlier, where my initial velocity in the x direction, so this guy here, ended up being about 61.97 meters per second. Notice I kept extra sig figs just for rounding errors later on. And my initial velocity in the y direction ended up being around 42.59 meters per second. But I'm not concerned with that now. All right, we have our diagram. The first thing we want to solve for, so part A asked for the maximum height. All right, so that's at this location here. So what I'm going to do is consider this to be my initial situation, and this is my final situation, the list of variables I'm going to make. So we're going to list our horizontal stuff and our vertical stuff. So horizontally, dealing with position, our initial position, I'm calling that 0. My vertical initial position is also 0. My horizontal final position, right, which is how far we travel horizontally to this peak, so that's going to be this location here. We don't know that value. Vertically, we also don't know how high we go, and that's going to be what we're interested in just a minute. I'm not going to circle it here just in case I want to use these this list of variables later on. I'm going to list my acceleration next. Horizontally, our acceleration is 0. Vertically, our acceleration is negative g. Right? So because our object is in free fall, the only acceleration we have is the acceleration due to gravity that has a magnitude of g. In the downward direction, downwards is negative in my coordinate system. My initial velocity in the x direction, I already found an expression for that. That's v naught cosine theta. Where my initial velocity in the y direction is v naught sine theta. Horizontally, since I'm not accelerating, my final horizontal velocity is the same as my initial. Vertically, I am accelerating, but we know since we're at the peak of our trajectory, the horizontal component of our velocity is just v naught cosine theta, and our vertical component is 0. All right, using this value right here, that our final velocity in the y direction up here is 0. That's going to be that's the key to solving this problem. And we are not given our time, but we do know the time it takes to travel vertically upwards this height is the same amount of time it takes for us to travel horizontally to this position. All right, so these times will be the same. So solving for our final height, think about our kinematic equations. There are two that contain y in them, or position, so to speak. That leaves us, let's see, the first kinematic equation, the velocity equation, does not have position, so that one's not going to work out. The second equation requires time, so the position equation requires time. We could solve for time and do that, or we could jump to the no time equation, which is what I'll do here. So the no time equation says that our final velocity in the y direction squared is equal to our initial velocity in the y direction squared plus 2 times our acceleration times our change in position, i.e. our displacement. So here's my equation. I'm going to plug in my zeros. So we have decided that our initial position we're calling 0, and we also know that our final velocity vertically is 0. So that leaves us with 0 is equal to our initial velocity in the y direction squared plus 2 times my vertical acceleration times my final height. We are solving for this value here, y, so I'm going to rearrange and solve. So first I'm going to bring over this term to the left-hand side. So I have negative initial velocity squared is equal to 2 times my acceleration times my final vertical position. All right, now I'm going to bring my 2a over to the other side, do that by dividing. All right, and when I first look at this, I think, uh-oh. It says my final height is a negative quantity. I'm calling upwards being positive. If upwards is positive, this should be a positive value. Luckily, that's not an issue because when we plug in my acceleration is a negative g, so that cancels out. So I'll do that here. So this is my initial velocity in the y direction squared divided by 2g, so that negative sign cancels out. So we plug in these values here, and well, initial velocity in the y direction, that's just initial velocity sine theta, that whole quantity squared, divided by 2g. Doing that computation, we find that our final height is about 92.5 meters, and that's using g being 9.8 meters per second squared. Okay, yay, we did it. We found our final height. B asks for the total time in the air. So there's two ways we could solve this. We could solve for time considering this to be our initial position, this to be our final position. That's all fine and dandy. I am going to use a trick, not a trick, I'm lazy. I already have my horizontal and vertical stuff listed for calling this to be my final position. Because of symmetry, we know the time it takes for us to travel to our peak here is the same amount of time it takes for us to travel back to the same height on the other side. Right? So a total time in the air is going to be twice the time it takes to get to our peak. So essentially, we're going to solve for the time it takes to get to our peak here, basically this time. Let's move this up. All right, so solving for that time, it's going to be simplest here, given our information that we know. I'm going to use the vertical stuff and use the velocity equation. All right, so that states that our final velocity in the y direction is our initial velocity in the y direction plus our acceleration in the y direction multiplied by time. Plugging in our zeros, initial velocity in the y, that is 0. That's the only 0 we have. So 0 is equal to our initial velocity in the y plus acceleration times time. Now I'm rearranging, solving for time. That's the expression I get. Right, so I brought this over, it brings me my negative, then I divide by acceleration on both sides. Plugging in our known values, we have negative initial velocity in the y direction. That was just our initial velocity times the sine of theta. And that quantity is divided by our acceleration in our vertical direction. That was negative g. Negative signs cancel. Plug in our values here, and we get that this time is about 4.346 seconds. All right, great. That is not our answer, right? Since that's only the time it takes to get halfway over. So to make the full amount, you multiply this number times 2. And that gives us about 8.69 seconds. All right, so that's the time it takes for us to travel our total distance here. Part C asks for the total horizontal distance covered. All right, so in this part here, we can simply, so now we're considering this position here to be our final location. So we can consider this to be initial, this to final. You can also consider this initial, that's final. It'll all work out. I'm going to say this is my initial now, and this is my final. So in doing that, we have actually already found the time it takes to do that. Right? We found that to be 8.6269 seconds. Right? So we know the time it takes to go all the way across. We know our initial velocity in the x direction. And basically, so I'm not going to relist all the variables for the sake of time, but we can use our position equation. So that says that our x, our range, is going to be our initial position plus our initial velocity in the x direction times time plus 1/2 our acceleration in the x direction times time squared. Plugging in our zeros horizontally, we don't have acceleration, and we said our initial position was 0, so that's where the ball was fired from. So how far we go is just going to be our initial velocity in the x direction times time. Our initial velocity in the x direction, that's v naught cosine theta, and we multiply that by time. All right, the reason why I wrote those extra parentheses because it might have been confusing with theta and t next to each other. I probably should just put parentheses around the theta for the argument of cosine, but too late. Plugging things in here, right? So v naught, you plug in the angle theta, you plug in t being the 8.69 seconds to get our total range across. And once you do that, we get about 539 meters. All right, we found our range. The last thing we need to do is find the velocity of the projectile 1.5 seconds after firing. All right, so that's part D. So we know our time. The time we're dealing with now is 1.5 seconds. If we consider, again, this to be our initial position, we are now analyzing some moment. Probably it's going to be a longer path here since we know it takes 4.3 seconds to get up here. So we're analyzing our final position somewhere around here. So kind of sorry for a sloppy diagram here. But I unfortunately have to finish this quickly to be posted on YouTube. So anyway, so we're considering that our final position. So we need to find our final velocity. And the way we're going to do that is solve for our final velocity both in the vertical and horizontal directions. Well, one of those is a known value, but anyway. And then we're going to vectorially add them. So thinking about things horizontally, our initial velocity, which is the same value you had before, that is the same thing as our final velocity. So our velocity after 1.5 seconds, right? And that was our v naught cosine theta. All right, so that's going to be useful there. I'm going to crunch these numbers just for the sake of your confusion. So when we crunch this out in the x direction, let me look at my notes. I said them orally before. Let's see. This was 61.97 meters per second. We also need to solve for this vertically. So our final vertical speed, we can use the velocity equation. So our final velocity in the y is our initial velocity in the y plus acceleration times time. in this situation, right, this time our final velocity is not 0. This is with the velocity after 1.5 seconds. So plugging in numbers here, our initial velocity in the y, that's just v naught sine theta, plus my acceleration is negative g, negative 9.8 meters per second squared, times the time of 1.5 seconds. Crunch that all out, and we find that our vertical component of velocity after 1.5 seconds is 27.89 meters per second. All right, so we have our x component here and our y component here. So now we use a little bit of trig. Let me go actually I'm just going to work here, saving paper. So using a little bit of trig here, we want to find what our resultant vector is. That's going to tell us the speed at that location. We're also going to specify the angle because we're dealing with, it's asking for velocity. We just found that this leg here has a value of 61.97 meters per second. This leg here has a value of 27.89 meters per second. And this angle here is an angle we want to find. So we want to find the length of this here, so to speak, and that angle. You guys can probably see we have a right triangle here, so we use the Pythagorean theorem to solve for our resultant velocity, right? So a squared plus b squared equals c squared. So my velocity is going to be the square root of each of these legs squared. So that's 61.97 meters per second squared plus the 27.89 meters per second. Squared. That whole thing is square rooted. Sorry for being kind of sloppy there. And we find that this speed is 68, or approximately 68 meters per second. All right, so that's the speed at which we launch at. Since it's asking for velocity, or sorry, not the speed at which it's launched at, that's the speed of the projectile at this location after 1.5 seconds. But we also need to find the angle here to specify the velocity. So we can use that using the inverse tangent function. So theta is going to be equal to tangent inverse of opposite over adjacent. All right, so that's going to be Vy is the 27.89, Vx is 61.97. Do that computation and you get this value is about 24 degrees. All right, so our velocity of our projectile after 1.5 seconds is going to be a value of 68 meters per second at an angle of 24 degrees. Oops. Thank you.